chemical kinetics, which is the last chapter here. And when we talk about kinetics, really kinetics deals with really how fast or slow a reaction takes place. And that's different than something you'll talk about when you get to 200B, which is sort of thermodynamics, which they kind of took out of this class here. Thermodynamics really deals with the idea of whether or not a reaction will take place. Really what we look at in there is the idea of sort of, will a reaction be spontaneous or non-spontaneous? And when we talk about thermodynamics, which is coming up in 200B, if you are taking that, that is sort of what we look at, whether or not a reaction is sort of spontaneous under those conditions. And sometimes people, when they think about the word spontaneous, associate it with sort of the rate of a reaction. And what you'll learn is a spontaneous reaction could be really fast, but it could be really slow. And a spontaneous reaction really just means that under those conditions, you would expect that reaction to occur. And like I said, it could be really fast that it occurs, or it could be really slow that it occurs. So really the study of kinetics deals with really the idea of how fast or slow a reaction will basically take place. So when we talk about kinetics, we oftentimes talk about a rate. And in terms of sort of reactions that take place, what we're usually interested in is a lot of times is sort of the change in the concentration. Again, the brackets there mean concentration, and usually that will mean molarity, which is our moles per liter. So a lot of times we look at really how the concentration of either a reactant or a product is changing with time. So that is usually the sort of thing that we look at. And that is why we typically will have reaction rates that have these type of units of molarity over seconds. It kind of tells us, again, how the concentration is changing over a period of time. So when we look at a reaction, just a simple reaction like what we have there, A going to B, we would expect this reaction to head in the forward direction here. And that would mean that as the reaction is taking place, we would expect that the amount of A should start to decrease. And as we are starting to form our products, we should expect the amount of B to start to increase. So we can write what is sometimes referred to as the rate expression, which are these guys here. And that is, for example, the rate is equal to negative the change in the concentration of A over the change in time. So kind of final minus initial on both of those guys. We do insert here the negative value in this one because A is a reactant. So because we would expect that the concentration of A will decrease with time, we do have that negative value there. And that is because when we calculate the rate, it typically should be a positive number. So we should get a positive number. Why that's important is, for example, if we just simply look at A going to B, and if we initially started out with like 4 of A and nothing of B, and as the reaction took place and ended, maybe we had 2 of A left, and maybe we made 2 of B. If we were to do the change in the concentration of A in this case, it would be final minus initial, which would give us a -2. So that minus and that minus will come together to make the rate overall for the reaction become a positive number. So that is really why the negative value is there for any reactant, because they should be decreasing with time. We do not see that when we get to the product side because they should be increasing with time. So we have basically the same thing. The rate here is equal to change in concentration of B over the change in time. If we just use my simple example here, if we did our change in the concentration of B, it would be final minus initial, which would give us a +2. And again, that's why we do not have the negative here. So when you typically calculate reaction rates, they typically are positive values. And then to ensure that you do get a positive value, especially if you're doing some type of rate expression for a reactant. That's why the negative is there, because it's decreasing with time as the products are increasing with time. Questions on that there? Now, we can definitely follow the change in the concentration of A over time. And as we can see here, if we look at our circles, and A is all the black circles here, is obviously at time 0. We have pretty much all reactant molecules. As the reaction starts to proceed with time, we start to see our reactant molecules being replaced by product molecules being formed, which is our red circles. And towards the end of the reaction, we have a lot of obviously our products that have been formed. We see that graphically as well. In kinetics, they like nothing more than graphs all the time. When we look here at the very start of the reaction, we have pretty much all reactants, no products. And as the reaction proceeds, the reactants are turned into products. So we start to see an increase in the amount of products that are being formed. So obviously we made a good amount of products at that point, and at some point, right, the reaction will pretty much sort of die down. One way you could kind of follow a reaction rate is by observing something like a color change. So if you do have a reaction where there is some type of color that occurs, either maybe the reactants start at a certain color or the products become a certain color, you could use something like a spectrometer, like we did with our spec 20, to really follow the absorbance values here, and use something like Beer's law, where A is equal to B times C, where A is absorbance, B is Beer's constant. We did that, I think, with the Kool-Aid experiment, and C is our concentration. And basically in this case, the BR2 is this sort of color here. So definitely at the start of the reaction, we pretty much have reactants, as we see by the color. As it kind of rolls to our products here, these guys are pretty much colorless. So as we start to see a decrease in the color here to pretty much colorless, we know that we are converting reactants into products. And we could use something like a spec 20 to follow the change in absorbance values, because the absorbance would be proportional in this example to the amount of BR2 that's present. Absorbance works because the darker the color, right, the more absorbance you have, right? The lighter the color, the less absorbance that you had. And you should remember a curve like this if you were like the spectrometer master. Is that what they called you in that experiment? So this is right where we choose our maximum wavelength, right? To set like our spec 22 or spectrometer 2, we would want to choose somewhere where we have pretty much our maximum absorbance. And that is so that when we run our samples, we should get all of our values to come out. Again, if we were to choose a wavelength over here, we pretty much have just that amount of absorbance available to us, which means most of our samples would definitely be off in the scale. So we also talked about the idea, right, that the color that we see in the solution, right, is complementary to the color of light that's being absorbed. So that's why, again, when you would select a wavelength, it wouldn't necessarily be the wavelength, like for example, we use red. It wouldn't be the wavelength for red, but more on the complementary color to red side is what you would just basically set it to. So by following the change in absorbance values over time, we actually can basically get some kinetics data, because again, we can relate it back using something like Beer's law to figure out how the concentration of BR2 is changing with time. So that's a very common sort of kinetics experiment that's done, where you basically just kind of follow that change in color. Now, there's a couple of different types of rates that we sometimes look at, and you could graph this. This is the example we were just looking at. And you can see over time here, we see the concentration of BR2 is dropping with time. You could take the slope of the tangent of each of those lines, which sounds very calculus-like, and to figure out basically sort of an instantaneous rate versus an average rate. A lot of times what we are looking for in sort of kinetics is the average rate over the whole entire reaction. So you can kind of think of it like this, if you drove, say, from here to, say, Arizona or something like that, on average, maybe you drove 65 miles an hour, all the way there. But maybe there's points there along the way, right, for sort of a window of your trip that maybe you're doing 70, 75, 80, 85, not 90, I hope. But there might be a window there. Well, I guess it's 75 once you get into Arizona, so it's not too much higher than that, but you shouldn't go higher than that. But there could be a window, obviously, where you're traveling a lot faster, right, for a period of time. But if you sort of average your whole entire trip, maybe you really did keep it about 65 or for your whole entire trip. So that's sort of the difference between sort of an average rate and an instantaneous rate, which is basically a rate for a specific period of time. That sort of instantaneous rate would be like if we're just looking for just this portion of it, it may actually be changing faster than maybe this portion is changing. But if you took the average rate over the whole entire haul, you would basically average everybody out. So a lot of times we do look at the average rate. And again, that's basically found by taking your final concentration minus your initial, and obviously your final time minus your initial time. Once again, the top here would typically be molarity and the bottom would be seconds to give you that average rate. Once again, this value here should usually be a positive number when you do calculate it for the reaction. Now, there is a relationship that does sort of vary. So as we were just seeing, if you sort of take that instantaneous rate for just say a period of time, there are different rates that basically occur, those initial sort of rates. But there is a relationship if you take something like this guy here, which is what is sometimes referred to as a rate law. Something written like this is what is referred to as a rate law. And if you solve for K, in this particular case, you can take the rate divided by the concentration of Br2, and K here is what is known as the rate constant. And the rate constant, as we can see from this table, gives us, as you see, a constant value for the rate of the reaction, regardless of sort of what period of time you're looking at. So the rate constant, in essence, will tell you sort of how fast or slow the reaction is progressing. If you have a large value for the rate constant, then the reaction is probably proceeding fairly quickly. If you have a relatively small value for the rate constant, then it's proceeding a little bit slower than normal in this case. In this case here, with something like 3.5 times 10 to the minus 3 reciprocal seconds. The rate constant is also important, as we'll talk a little bit about in this chapter, probably. The actual units associated with it will tell you, bless you, what type of reaction you're dealing with. And for example, these are reciprocal seconds, the units for the rate constant. And that's typically, as we will see, what is referred to as a first order reaction, which is typically kind of a lot of times one reactant or maybe two reactants at most that are reacting is a first order sort of reaction. So as you go through kinetics problems, sometimes they will just give you sort of the value of the rate constant and the units associated with it. And a lot of times that does give you some information about what proper formulas that you should use based on the value of the rate constant that you see. Now, if we happen to have a reaction where we maybe don't have any type of colored product that would be made, and maybe it's all gases here, as we can see, we could also sort of do a rate study by looking at pressure here. So in this case, the only gas that's present is oxygen gas. So we could use something like the ideal gas law there, and kind of like what we talked about when we were talking about gases, is if you solve for N over V, that equals P over RT. And remember that when you do solve for N over V, that is basically moles per liter, which is basically molarity. So in a simple experiment, you really can just follow the change in pressure. The temperature probably would be held pretty constant in that experiment that you did. And really just by following the change in pressure over time, you could do some calculations and really relate it to how the concentration of the gas is changing over time. In this example here, the only gas present is oxygen. And the only way to get pressure would be oxygen would have to be made in this case, right? So it has to be a product that had to be made to account for the pressure. So in this simple experiment here, even though you may not have color and use like a spectrometer or something like that, you again follow the pressure and relate it back and figure out the rate by simply following the pressure over time and you'll be able to really see how the concentration of O2 changes, and that's how we would get to kind of the molarity of it. So when we do look at reaction rates and reaction expressions, we do need to take into account always sort of the stoichiometry of the reaction, because it does have an effect obviously on the rate of reaction and how everybody's reacting. So obviously, if we look at this equation, our basic stoichiometry relationship is 2 moles of A gives us 1 mole of B. So when we write our rate expression for this reaction, we do want to sometimes take into account, or all the time, take into account the stoichiometry. And you actually can do that as part of the rate expression. So that is really where the 2 comes from, is basically 1 over the coefficient. So the coefficient here in A is 2. So we take 1 over the coefficient, and really what that does is it takes care of the mole to mole relationship, or the stoichiometry for that reaction if you're going to do some calculations. Again, we still have our negative because it's a reactant, the change in the concentration of A over the change in time. When we get to B, the coefficient is really 1. So that's basically 1 over 1, which is why there's no number there. And that again would give us the change in the concentration of B over the change in time. So in general, if you have a reaction and you want to figure out how everybody in the reaction is changing, you can write this rate expression. The rate would equal, again, our reactant, negative 1 over the coefficient, change in concentration of A over change in time, and that would equal minus 1 over B, the change in concentration of B over time. Now, when we get to our products, we have no negatives there, so 1 over the coefficient for C, and the change in concentration of C over time, and our D. They all equal each other, and they all equal the average rate for the reaction. And what that allows you to do is, frankly, if you know basically one piece of information, maybe you know the average rate, or maybe you know how D is changing with time or something like that, you could then use this relationships here basically to figure out how C is changing, B is changing, A is changing with time. And if you do 1 over the coefficient, that will again take care of really the stoichiometry part. In reality, if you do some calculations using this, you could just do kind of like a stoichiometry problem first and then kind of incorporate it into the kinetics. It does work the same way, but sometimes it's easier just to kind of do it all. Okay, so let's take a look. So we could write the rate here would equal, starting with our first reactant here, it would be negative the change in concentration of CH4 over the change in time. Here, the coefficient is 1, so we don't need to worry about the 1 over the coefficient. That would equal our second guy, which also should be negative, but it does have a coefficient, so that would be 1 over 2, the change in the concentration of O2 over the change in time. Coming to our product side, these guys should be increasing with time, so we don't need a negative. Once again, here the coefficient is 1, so it would just be the change in concentration of CO2 over the change in time. And lastly, here for our water, we have a coefficient of 2. So 1 over the coefficient, change in the concentration of water over the change in time. So this would be really the rate expression for this reaction. And again, if you, for example, had some information about water here, how it is changing with time. So maybe you knew that, you could basically just pull out the parts that you need. Maybe you want to know, how this guy is changing with time. So you can just pull out those 2 things. For example, the rate is equal to minus the change in the concentration of CH4 over the change in time. You could also say the rate is equal to 1 over 2 change in the concentration of H2O over the change in time. So again, let's just say we actually knew what this value was. That would allow you to actually figure out the average rate. And why that's important is that rate there would be the exact same rate that's here. And that would allow you to figure out, for example, how that guy is changing. So you could pull out the parts that you need. You could use one piece of information to figure out the average rate, and then use the other relationship to basically figure out how things are changing. So for example, if this was like 4 molar seconds, how that's changing. We know that we could put in there the rate would equal 1 over 2 4 molar seconds. These guys would cancel. and we would end up with 2 molar seconds as our rate. Then we would know that if we took this rate, which is positive, and stick it in there, we would have 2 molar seconds equals minus the change in the concentration of CH4 over the change in time, which means really the only thing that would come over to the other side is the negative, and that would be negative 2 molar per second would be how the methane here is changing per time in my made up example. This would be a negative because, again, methane is a reactant, so it's basically decreasing by 2 molarity per second is basically what that means in this particular reaction is how it's basically changing. So that's how you can sort of use each of the individual guys. And again, we could relate it to everybody else that's there by using that rate expression. Any questions on that there? All right, so why don't we try one with actual numbers here. For this reaction, the concentration of I minus changes from 1 molar to 0.868 molar in the first 10 seconds. What is the average rate in the first 10 seconds? And we are also looking for how the concentration of H plus over time is minus. We have the initial I minus, which is 1 molar. We have the final I minus there, basically, which is 0.868. Obviously, here we're doing 10 seconds, so initial time would be 0. Final time here would be 10 seconds. And we're interested, obviously, in I minus. We're also are interested here in the H plus. So really, we could just pull those two things out of the rate expression here. We don't really need everybody else. If we look at the rate expression, we've got the rate is equal to minus 1/3 for the coefficient there, just for the I minus, the change in the concentration of I minus over the change in time. We also could pull out our rate expression for the H plus, and that would be the rate is equal to minus 1/2 for the coefficient, change in the concentration of H plus over the change in time. Again, both of these guys are reactants, so they're decreasing, so that's why we have our negatives. We really have the information here for our I minus, so we can put that information in. And if we do that, we get that the rate is equal to minus 1/3. We'll do our final concentration, which is 0.868 minus our initial, which is 1. And really kind of 10 minus 0 seconds. This obviously is going to give us the negative that's going to go with this negative and turn our rate into a positive number, which is what it should be. So again, when you have that reactant, it should be a positive number for the rate, 0.868. If I punch it in right, maybe 0.868 minus 1 divided by 10 and divided by 3. That is going to give us a rate or average rate of 0.0044 molar seconds is our average rate. That on average is how everybody is sort of changing concentration per second over that period of time. Any questions so far? Yeah. I'm sorry, would what? With the numerator, are you talking about like when we get the final answer? Is that what you're talking about? Or? Yeah. The numerator would never be anything but 1. Numerator is the way on top, right? So the numerator will always be 1. Don't use those fancy math words with me. No, numerator will always be 1. The denominator is basically the coefficient. So yeah. So that's basically how you get sort of the proper mole-to-mole relationship is to take 1 over the coefficient. Yeah, and that gives you basically the kind of proper 2 moles to 1 mole relationship when you basically do the math part of it, which is what we're going to do right now. But yeah, the numerator will always be 1 and the denominator will always be the coefficient. Sometimes you may not see it in there because the coefficient is 1, so it's basically 1/1, and that's why sometimes it doesn't. The average rate should always, in this case, is molarity per second. Yeah, so that's concentration over time. It will, in most cases, it will be that molarity per second. It could technically be something else like atmospheres per second or pressure, but usually molarity per second is what we look at. But it should always be a positive number when you do calculate the average rate. Other questions? So now that we have this rate, that rate is actually this number right here. So now by using that information about I minus, that actually gives us that value up there. And the rate here would then equal -1/2, change in the concentration of H plus over the change in time. So in this second part of the question, we're really looking for this guy right here. So we're really looking for what that value is. That means that we want to put in our number, which is 0.0044 molar seconds, would equal -1/2 change in the concentration of H plus over the change in time. That means we need to actually multiply the 2 to the other side, and that's really taking care of the stoichiometry, the relationship there, basically the 3-to-2 relationship. We're going to multiply the 2 to this side, but not just the 2, also the negative needs to come for the right as well. So when we do that, that will then get us that the change in the concentration of H plus over that time basically will equal our 0.0044 times 2. Gets us our -0.0088 molar seconds in this case. Here we do want the negative because it's specifically talking about our reactant, which is H plus, that is decreasing with time. So that's what the negative basically says. On average here, our H plus is actually changing basically 0.0088 molarity every second, which if you look at the average rate for everybody, it's working like twice as hard, right? Basically, right? So it's doing twice as much as the average rate that's happening. And again, that's, some of it to do with sort of the stoichiometry and the multiple relationship that is present. Any question on that? Yeah, this top number you're talking about? Yeah. So that would be the average rate for the overall reaction, how basically on average everybody's changing in terms of their concentration, kind of for the whole ride. Specifically speaking, if you were interested in this question like we were here, this is specifically how the H plus concentration is changing with time. And it's basically decreasing by 0.0088 molar every second, basically. So it's losing that much molarity every second as it goes through that reaction. Other question? All right, let's try another one here. If 2.4 times 10 to the 2 grams of NOBR, molar mass 109.91 grams per mole from the periodic table, decomposes in a 2 times 10 to the 2 milliliter flask in 5 minutes, find the average rate of BR2 production based on that equation that's there. Okay, let's take a look. So we obviously have information about NOBR. We're looking for BR2. So again, we can really start with our rate expression and pull that information out. This would be -1 over the coefficient there, change in the concentration of NOBR over the change in time. We also can do our BR2 here, which would be the rate is equal to change in the concentration of BR2 over the change in time. Once again, here the coefficient is a 1, so basically it's 1/1, so you don't really need to put it into the expression at that point. We do have information here to really figure out the molarity of the NOBR as it decomposes, and we also have the time information as well. So since we are looking for eventually the time in seconds, we might as well just get that out of the way and convert our minutes into seconds. So there should be 60 seconds. So that's 300 seconds. We also need to find the molarity. So we can find the moles of the NOBR by taking 2.4 times 10 to the 2 grams using the molar mass, which they gave us, which would come from the periodic table. 109.91 grams per mole. That gets us about 2.1836 moles. We are also have the volume here which is basically 200 milliliters, which if we convert to liters, which is what we need for molarity, would get us 0.2 liters. So we have the volume and we have the moles. So that again is how we're going to get our molarity here of the NOBR, which is really how it's changing this concentration, which would be our 2.1836 moles divided by our 0.2 liters. Gets us a 1092 molarity. And we also have our seconds. So we basically now have the molarity. We also have the seconds. So we do have everything we need now for our NOBR. If we put that in there, the rate would equal -1/2 negative 1092 molar over 300 seconds. Why did I make it a negative? Yeah, so it's a reactant. So technically the way we got that number would have been final minus initial, which should always give us a negative value, right, for the change in the reactants concentration. And again, that negative will obviously put that negative into a positive value for our rate. So if we do that, we'll take that divided by 300, also divided by 2 in this case for the stoichiometry, will give us a rate of 0.018, call it 2 molar seconds. Question? Yep. No. At this point, that is the rate, and we are looking for really this right here, which is how the BR2 over the time is changing. So that is the rate is equal to the change in concentration of BR2 over the change in time, which frankly means that is that number as well, right? That goes right in there. And that would get us how BR2 over the change in time is changing on average as well. Basically the same as the average rate is changing, because the coefficient there is 1 basically. So it's changing just like the average rate of the reaction. Any questions on that there? Any questions on rate expressions, how to use them to figure out any of those things? We would again use rate expressions to figure out reactants, products, how everybody is changing. Sort of a convenient way. Like I said, you basically just need one piece of information and then pretty much you can get everybody else's. This is also makes sense because this is a product. So again, we do end up with a positive value for how it's changing. So it should be increasing with time. All right. So let's talk a little bit about some factors that do affect reaction rates. The nature of the reactants, what physical states they are in, has an effect on the overall sort of rate of a reaction. If you have smaller molecules, they do tend to react faster than larger molecules. Gases tend to react faster than liquids, which obviously react faster than solids. And that's just the idea of energy, right? So gas molecules are constantly flying around. They have a lot of energy, which means they tend to react pretty easily. Liquid molecules still have a good amount of energy as they're moving between each other and moving around. And obviously, when we get to solids, they lack a lot of energy, so they tend to react a lot slower. But solids do react. Powder solids are more reactive than block solids. It's kind of more surface area. So if you spread it out, you get a little bit more reaction in areas where it can react. Certain metals are more reactive than others. So if you remember when we talked about single replacement reactions, there's an activity series of metals, which, you know, for example, hydrogen's in the middle and a bunch of metals above it, a bunch of metals below it. Anything higher on the list is more reactive than anybody lower on the list, and vice versa. Anybody lower on the list is less reactive than anybody higher on the list. Ions as well, they tend to react faster than molecules because, frankly, if you are an ion, that means you are frankly floating around in the solution ready to go. So, you know, you're ready to react and you don't have to worry about any type of bond being broken. You're basically floating around ready to do the reaction. Temperature plays an enormous amount of effect on reaction rates. So typically when you increase the temperature, everybody pretty much gains more energy. It allows barriers to be sort of overcome. And you typically will see an increase in the rate of the reaction on general, but not for all reactions, but a lot of reactions, if you just simply increase the temperature by about 10 degrees Celsius, you typically can expect sort of a doubling of the rate of that reaction. Vice versa would happen as well if you obviously put everybody sort of on ice and kind of lowered the temperature. Everybody has less energy, so you have a lower proportion of molecules that have enough energy really for the reaction to take place, and you typically will see sort of a decrease in the rate of a reaction. As we'll see in this chapter, there is what is referred to as the activation energy, which is the hill that everybody has to sort of climb to get on the other side for going from reactants to products. So the amount of energy that the reactants have, there's only a certain amount of molecules that have enough energy really to get up and over that hill to the other side. So obviously when we increase the temperature, we're getting a greater proportion of molecules that will have enough energy basically to climb that hill to get to the other side to make products. And obviously when you lower the temperature, you're going to have a lower proportion of molecules that have sufficient amount of energy basically to get up and over the hill to the other side to make products. And that affects obviously the rate that we see. There is a relationship that we'll see in this chapter that does relate temperature to reaction rate. The other thing that really affects the rate of reaction are catalysts. Catalysts are not reactants. They're not products. They're there simply in most cases to facilitate the reaction occurring faster. They typically are found a lot of times in reaction or equations written on top of the arrow. So maybe it's a metal, maybe they write something like H plus on top of there, maybe they put a metal or something like that. And these catalysts do not get used up in the reaction, but they really do just sort of facilitate it occurring faster. And that's usually most of the time when people talk about catalysts, what they're talking about sort of speeding up the reaction. There are some negative catalysts that can actually kind of slow down the reaction, but most of the time, if somebody's talking about a catalyst, they're usually talking about it in terms of it speeding up the reaction. How do they do that? Well, some catalysts are homogeneous, which means they're in the same phase as what's reacting, and some are heterogeneous, which means they're in different phases. So for example, metal can be used as a catalyst, and perhaps the metal maybe attracts the gas molecules to it, and that allows those gas molecules to come together in a lot more efficient manner to sort of start the reaction than if the metal wasn't there and they're just flying around trying to find each other. So a lot of times the catalyst almost serves as like a central location for everybody to come to, and also helps in sort of the reaction to take place a lot more efficient. So usually catalysts will find sort of an alternative approach to the reaction. And by doing so, what it essentially does, as we'll talk about, is, as I just mentioned, that sort of hill, that activation energy hill that everybody has to climb. By using a catalyst, it's actually able to lower that hill in terms of energy demand. And because of that, you have a greater proportion of molecules that can then get up and over to the other side. And again, that usually will result in a much faster rate occurring. The concentrations are really important. The larger the concentration of reactant molecules, the faster the reaction takes place. An increase in frequency of the reaction taking place. When we talk about concentration, it really is molarity, which is really moles of solute per liter of solution. And if you remember, a solution is made up of two things, the solute and the solvent. And when something is reacting, is it the solute or the solvent that's really doing the reacting? Is really the solute that's really reacting. So when we have a larger concentration, the only way to get a larger molarity is if this number is bigger. That means we have a lot more solute molecules in there, and that will increase the rate of the reaction. In terms of gases, concentration depends on the partial pressures of the gas. At higher pressures, we have a higher concentration of gases, because also at higher pressures, we have a much smaller volume, right? Which means the gas molecules are pretty much right on top of each other. So that's definitely going to increase the rate of the reaction to take place. Obviously, the opposite would be true if you kind of had a lower pressure, larger volume. Again, it's going to take a little bit longer for everybody to sort of find each other, and that would slow down the rate of a reaction. Any questions on any of those things there? All right, so we talked about the rate expression. We're now going to talk about the rate law, which is a little bit different than the rate expression in some aspects. The rate law expresses the relationship of the reaction to the rate constant for its reactants raised to some power. So for this reaction, this would be our rate law. The rate, which is something like molarity over seconds. That is our rate constant, which is that constant value that happens as long as you don't change the temperature. This is the concentration of A and the concentration of B. X and Y are what are referred to as orders. So X is the order with respect to A in this example, and Y is the order with respect to B. You can find the overall order of a reaction by simply adding those two together. So if X was 1 and Y was 1, then the reaction would be second order. If X was 0 and Y was 1, it would be first order overall. The orders are sort of the proportion that you need of each of those reactants to basically get a specific rate to occur. So orders are not the coefficients. So orders and rate laws are only found experimentally. So basically, orders, rate laws are found experimentally, which means they typically will give you a table, and you'll also use that table to basically figure out the orders. And then once you figure that out, you can actually figure out what the rate constant is. So how does like the orders maybe affect the rate of the reaction? So let's just say, for example, we did our calculations and we found that X was first order and Y was basically first order. And let's just say that we had a reaction where we had a concentration of A that was 2 molar and a concentration of B that was also 2 molar. And in this particular reaction, basically, we don't really know what the rate constant is, but it doesn't really matter. You basically get something like 4 molar seconds as a rate. So if we wanted to speed up this particular reaction, we could maybe double the concentration of A. So if we double the concentration of A in this case, that would give us 4 times 2, which would give us 8 molar seconds. In this situation, we also could have doubled the concentration of B and ended up with the same. The difference by doubling the concentration meant that the rate also doubled in this case, right? So maybe this reaction is too fast for us to basically observe while we're doing this reaction. Maybe we want to actually slow down this reaction. So maybe we cut the concentration of A in half, and then that would get us the rate is equal to K times 1 times 2, which means we would end up with basically 2 molar. We would cut basically the rate of the reaction in half, and maybe that would allow you to observe what you want to observe. Sometimes a reaction happens so quickly, and if you're trying to do a reaction or an experiment, by the time you get it into whatever you're trying to get it into, it may be too fast and the reaction's over. So a very common experiment I do at other class schools is a kinetics experiment where they take 2 solutions, they mix it together, and makes a color. They're supposed to swirl it and then put it into like a spec 20 to take absorbance value. Now, what happens is this reaction that they chose, which is not the best reaction, but the one that they chose is actually a very quick reaction. So when people put it together, they do the mixing. By the time they put it into the machine, the color is pretty much gone. Or if they're quick enough, they catch the back end of the reaction where there's really no absorbance and like the reaction is pretty much done. And then they raise their hand and go, what's happening? Like my patient died. My line is just flat. There's no absorbance values or anything like that. And it's really because the reaction is happening too quickly. So if we wanted to maybe give people more time, we could cut the concentration down and we could actually, slow down the reaction and maybe give them more time. Now, in this example, they both basically have an order of 1. And basically by changing one concentration or the other, we basically can double it. If we double the concentration, basically have it if we half the concentration in terms of the rate. But let's just say, for example, that we did the calculation and X was 1 and Y was 2 in this particular case. So if we wrote our rate law here, it would be K times A and B would be squared in this case. Now, if we did our same concentrations that we did originally here, which was 2 molar each, we would have 2 molar and 2 molar squared. That would give me 4 times 2, which would be 8 molar seconds. So right off the bat, in comparison to this reaction versus this reaction using the same concentrations, we have a reaction that's occurring twice as fast, right? Because the order of B is actually squared. In this case, though, if I doubled the concentration of B, and I did that and kept my A constant and doubled my concentration of B to 4 squared, that's 8 times 2 would give me 16 molar seconds. So the reaction rate here is, that would be some bad math, I know. That's 4 squared, be 16 times 2 is 32. I know, I can do math, sort of. That's good, I'm getting it. I didn't even pick up the calculator, that's good. In this case, by actually just doubling that, which seems a little bit better now with the right number there, by doubling the concentration of B in this case, the rate actually went up by a factor of 4 in this case, right? So the different reactants in different order, you know, the order is basically the proportion that you need to basically generate a certain reaction. And in this case, if we really want to slow down this reaction, we would probably want to cut down B's concentration. It would probably have a greater effect on the reaction rate than if we cut down A's concentration, right, in terms of the overall reaction rate. So that's sort of what the orders are. There's sort of those proportions that basically will generate a certain rate, and it's useful in real life because if you do know sort of the overall rate law, you could really sort of play with the reaction to sort of modify it to either make it happen faster, slow it down if you needed to, and things of that nature. Any questions on that? Yeah. I'm just making up those numbers. Yeah. So I just made up those numbers. Yeah, so I made up all these numbers. So I made up both of these numbers, but because A is 1, it's basically 1, and that's 2. And that's why we squared the second 2 here, but we didn't square this one because it's technically to the first power. And again, all those were just made up, just as some simple numbers to sort of illustrate with my bad math there that, basically by playing with those reactants, you can really affect sort of the rate of reaction if you kind of know the orders. In addition, the other really important thing about the rate law is it's all about reactants. There are no products in a rate law. So as you can see here, there's nothing to do with products. So when you write a rate law, it is definitely all just solely about the reactants. No products are in there. So how do we figure out these rate laws? So typically you'll be given a table like this, and these tables here are the concentration of our reactants and what are referred to as initial rates. Now, you could do this by just looking at the numbers and really figuring out what's happening, but most people probably more mathematical approach is probably the best thing to do here. And you could do this sort of mathematical approach of rate 2 over rate 1 is equal to K times A to the X and B to the Y. Okay, A to the X and B to the Y. So when we say rate 2 and rate 1, it doesn't mean that you go to the table and pick number 1 and number 2 out of the table. It basically means that you go to this table, which in this particular example has only 3 entries, but you may have a table that has 4, 5, 6, a bunch of entries. But what you're looking for is 2 entries where one of the concentrations remain constant and the other one varies, because we're going to do some math here, so we want just really one unknown. So what we're looking for is 2 entries where one of them stays the same and one varies. So if we look at 1 and 2, an example, this guy's concentration stays the same, but this one's basically varies. So if we write the generic rate law for this reaction, the rate would equal K times F2 to the X and ClO2 to the Y. So by choosing experiments 1 and 2 here, we could use that formula up on top to figure out the orders. So taking experiments 1 and 2 here, I am personally going to put the larger guy up on top. That usually will give you kind of nicer whole numbers. You don't have to do that. You'll just get some decimals, but you could use the larger number up on top. So what I'm going to do is take everything from number 2 and put it up on top. So the rate is 4.8 times 10 to the minus 3 molar seconds. That will equal K times the concentration of F2, which is 0.1 to the X. And for our 0.4 is 0.04 to the Y. So basically what I put up on top is all the information from entry number 2 in the table. I'm now going to put all the information for entry number 1 on the bottom there. So on the bottom, we'll go everything from number 1, which the concentration is 1.2 times 10 to the minus 3 molar seconds, K, 0.1 to the X, 0.01 to the Y. Yeah. So once again, everything up on top is experiment 2's information. Everybody on the bottom is experiment 1's information. And I chose to put experiment 2's on top because it has a larger rate. Now we're going to do some math here without the calculator and hope for the best here. So we're going to divide. When we divide that, I'm going to go with a 4. Now coming to the other side, up on top is a rate constant. On the bottom is a rate constant for the same reaction. A rate constant would be a constant number, which means I don't know what the number is, but the guy on top and the guy on the bottom should be the same number. So those should cancel. This is the order for this reaction for F2 on top and bottom. Once again, I do not know at this point what that number is, but it should be the same, which means this will completely cancel. And now here I'm going to do this guy, which will cancel to 4 to the Y. Yeah. And at this point, you could probably see that Y should equal 1 in this case. Yeah. By the way, if we didn't have pretty numbers of that, you could take the natural log of both sides and divide. So you could take the natural log of 4 equals the natural log of 4. That will bring the Y down. You can divide the natural log of 4 to both sides. You don't really need to do that in this case, but you get 1. If you don't have a pretty number, that's the way you can basically solve it if you would like to do so. That tells us that the order for Cl2 is basically first order. We then can go back to our table. And in this case, since we kept the F2 constant, in this case, we want to actually keep the ClO2 constant. And we could do that by looking at experiment 1 and experiment 2. Experiment 3 will keep the ClO2 constant, but vary our F2. So looking at experiments 1 and 3 in this case, once again, I'm going to put the larger rate up on top, which is experiment 3. So all of experiment 3 is going to go up on top here. That's going to give me 2.4 times 10 to the minus 9 molar seconds equals K times 0.2 to the X, 0.01 to the Y. So once again, that is everything that is for experiment 3 up on top. Experiment 1 will go on the bottom. 1.2 times 10 to the minus 3. I feel like I wrote 9 there, but that should be a 3. Molar seconds gives me a K. This is 0.1 to the X and 0.01 to the Y. So again, up on the bottom, or up on the bottom, down on the bottom there is all of experiment 1's information, and up on top is all of experiment 3's information. Now we'll do a little bit more math here. That's going to divide out to a 2. Once again, the K should cancel because it's a constant value. This guy here will give me 2 to the X, and this guy will completely cancel. Once again here, X would equal 1 in this case. They will not always equal 1, but it just happens in this case that it did. That is the order with respect to F2 in this case. We now actually have the completed rate law here, the order, so we can write the completed rate law, which means the rate would equal K times F2 times ClO2 would be the completed rate law. The overall order here of this reaction would be found by taking both of the orders and adding them together. So that is a 1 plus 1 equals second order reaction. So to find the overall order of the reaction, we basically just add our orders together. Now, once we have actually the completed rate law with the actual orders, we then could actually find the value of the rate constant. And to find the value of the rate constant, we could absolutely choose any one of the entries in this table and just basically put the information in and solve for K. So if I take my rate law, which is up here, and solve for K, the rate constant would equal the rate divided by F2 and ClO2. And once again, I could choose any of the entries in the table and put the information in. I'm just going to choose entry number 1, which means 1.2 times 10 to the minus 3 molar seconds divided by 0.1 molar divided by 0.01 molar. That is going to give me a rate constant for this reaction of 1.2 to the minus 3 divided by 0.1 divided by 0.01. 1.2, the units here are going to be molarity up on top and on the bottom cancel. 1 over molar seconds would be the units, and those are typical units of a second order reaction, which is what this one is, yes. Sit. How did I get to this? Is that right? Yeah, so I took the rate law here, the completed one with the orders, and basically I just divided all these guys to the other side. Yeah. Other questions? All right, so this is very typical of these sort of problems. As we saw there, our rate law always about the reactants, they're always found experimentally. And again, the orders are not the coefficients in the balance equation. All right, so why don't you try one here? Why don't you try this one here? Figure out what the orders are, the rate law, and the value of the rate constant. So give it a go. See what Okay, let's take a look since we're obviously it's the end here, a little overtime here. All right, so in this case, if we start with just the generic sort of rate law, the rate here will equal K times S2O8 2 minus to the X and our I minus to the Y. So once again here, we're going to look at this table and find two entries where one of the reactants stay constant. So 1 and 2 will achieve that for the S2O8. So looking at experiments 1 and 2 here, I am again going to choose the larger rate to put on top. So for me, I'm going to put number 1 up on top. That would give me 2.2 times 10 to the minus 4 equals K times 0.08 to the X, 0.34 to the Y. And again, that is all the information from experiment number 1. Experiment number 2 will go on the bottom. 1.1 times 10 to the minus 4. Our K, our 0.08 to the X, and our 0.017 to the Y. Here, that is going to give us a 2. Once again, the K's will cancel. These guys will completely cancel. And these guys here will give me a 2 to the Y. That means once again here, Y in this case would equal 1 for the order for I minus. Any questions on that one there? At this point, I'm then going to go back to the table. And now I really want to keep I minus constant, which means experiment 2 and 3 will do that for me. That will vary my other reactant. So looking at experiments here, 3 and 2, I'm going to put 3 up on top because it does have the larger rate. So everything from experiment 3 will go up on top. And 0.017 to the Y. Everything from experiment number 2 here will go on the bottom. 1.1 times 10 to the minus 4. And our k and our 0.08 to the x, 0.017 to the y. Doing a little math here, that's going to give me a 4 is equal to, these guys will cancel, these guys will completely cancel. That is going to give me a 2 to the x, I believe. In this case, x would equal 2. So it is second order with respect to the S208. Any questions on that one there? At this point, we now can complete our rate law here. Our rate would equal K times S2082 minus, and that guy was squared. And our I minus was to the first. That also means that the overall order of this particular reaction would be 2 plus 1, which would be a third order reaction in this particular case. Now that we do have the orders, we can use our rate law and solve for K and actually get the value of K. And in this case here, I'm going to take K will equal our rate divided by the S2082 minus. We do need to square it, and our I minus. Once again, you could choose any of the entries in the table because it's a rate constant. Each one should really give you the same value. So I'm just going to choose number 1 again. And when I do that, I will have 2.2 times 10 to the minus 4 molar seconds divided by our 0.08 squared and our 0.034 molar. And that should have a molar in there as well. When we do that, we will end up with 2.2 to the minus 4 divided by 0.08 squared and divided by 0.034. Going to give us a rate constant here of 1.01 units. Molarity on top and bottom will cancel. 1 over molar squared seconds would be our units that is left over at that point. Any questions on any of those? So that's a very typical type problem. Like I said, these tables only have 3 entries, but you may have ones with 4 or more, but you just really want to choose 2 entries at a time, one where it keeps one constant, the other one varies, and so forth. Any questions on how to figure out the rate law experimentally here? All right, we